And we are live. Okay, so I'm Doug. This is Mocha. This is Math with Doug, but more specifically, it's Geometry with Doug. And even more specifically than that, it is the Geometry of Composite Shapes with Doug. Okay, I'm going to put down the dog. You lie down. Lie down. That's right. Stay. Good girl. Okay, so she will get her supper when we are done. We have three composite shapes here. What are composite shapes? A composite shape is a shape that's made up by combining smaller regular shapes. So you can make all sorts of interesting shapes. When you combine the basic shapes that we have already worked with together, you can make all sorts of interesting things. So we have this. There is no area formula for this specific shape, nor is there one for this one, nor is there an area formula for this. So we have to break the shape down into its smaller shapes that were used to make it up in order to apply the area formulas for those smaller shapes and answer a question. So what is the area of this shape? We have to figure out, how did I make that shape? I'm using shapes that we have covered before. All of the shapes that we have covered before can be used in these questions. We have covered various types of triangle, two types of trapezoid, rectangles and squares and circles, and parallelograms. So any of those could happen. And we have covered the area formulas for all of those shapes. So let's get into it. I think I'm going to start with this one because it seems kind of straightforward and simple. What is this made up of? Now, at first glance, you could say, well, obviously it's a rectangle with a square sitting on top, and that actually is true. But we also want to make sure that we know for certain what the shapes are. And do we have all the information we need? So we can see that if this is a square up here, we know that the side length of it would be 6 inches, but do we know that for sure? Nothing is shown here or here or here. So sometimes we have to do an extra step just to make sure that we have enough information so that we can then apply the formula for the correct smaller shape. What I can see here is that this whole thing's height is 12 inches and this part is 6 inches. Therefore, I can do a quick little subtraction. 12 minus 6 equals 6. This 6 inches that I just found has to be the height of this little shape, which now gives me evidence that allows me to conclude that yes, indeed, it is a square. So that's 6 inches, this would be 6 inches, this little piece here would be 6 inches, but we have enough information when we know that top side is 6, this upright is 6, we proved that with this little subtraction. This is a step, and it's kind of a necessary step. It's one that people might want to skip, but I don't recommend skipping it, because in math you should be justifying what you do. But now that we can see we have a square and a rectangle, finding the area is just going to be a matter of finding the areas of both of those smaller shapes and adding them together. So the area of this composite shape will be equal to the area of a rectangle, which is base times height, plus the area of a square, which is side length squared. The base times height, well, what's the base? The base of the rectangle is the 18. And the height is this 6. So 18 times 6. And then side length of the square is 6, so that's going to be 6 squared. We're well on our way, we can finish solving this. What is 18 times 6? 6 times 10 is 60, 6 times 8 is 48. 60 plus 48 is 108. And then 6 squared is 36. 108 plus 36 is going to be 144 square inches. I did forget to point out that this was in inches, but we have the little inch symbol, so it was apparent. Okay, 18 times 6, 60. Yes, I like my answer. Okay, let's move on to this one. Now this one is in centimeters. In fact, it's the only one of the shapes I'm going to deal with in this lesson that I'm giving in centimeters. We have, it kind of looks like a trapezoid, like a right trapezoid, but it isn't. I'm missing something though. I meant to put these little symbols here so that we can see that these are indeed right angles. And in fact, I'll put one here as well. Okay, the question is a little bit more complete now. But it's still not a trapezoid because this is a 5-sided figure. 1, 2, 3, 4, 5. And trapezoid is a quadrilateral, a four-sided figure. So no, it's not a trapezoid. It is a composite shape. And what would I put together to make that? Well, I can sort of imagine that if I just draw a line that's parallel to this base, that I have a rectangle here in the lower part, and then what I have on the top part is a right trapezoid. So therefore, the area is going to be, and do I have all the information I need? No, I don't have all the information I need yet, so I don't want to do the area formula yet. For the rectangle at the bottom, yes, I have enough information. The base is 30 and the height is 10. But for the right trapezoid, that's the top part of this figure, I know that this small base is 20. I know that the big base, my dotted line, is going to be 30. But what is the height? It might seem obvious, but again, I want to prove it. So the total height of the shape, which is 20, minus the height of this little rectangle part on the bottom, which is 10, tells me that the height of the right trapezoid is also 10. Now I have enough information so I can do the area. The area of a rectangle is base times height, and the area of the trapezoid is 1/2 base 1 plus base 2 times the height. Let's fill these in. Base times height for the rectangle is 30 times 10. Okay, that's messy. Let me fix it. 30 times 10 plus 1/2. The bases are the 30 and the 20. 30 plus 20. And the height is the 10 that I figured out over here. Simplifying, 30 times 10 is 300. 30 plus 20 is 50. Okay, now I have a choice here. I can say half of 50, I can say half of 10, I can say 50 times 10. There's different ways of doing it because these three values are being multiplied. So we have choices and we will get the right answer. The 300 is being added to half of 50 is 25, and 25 times 10 is 250. I'll do it that way. 300 plus 250 is equal to 350, and it is centimeters squared. Remember, it has to be squared. It is an area that we are doing. We have inches squared for the first one, centimeters squared for this one. Now we can move on to this one over here. I didn't really leave enough room. So what I'm going to do is first, I'm going to take a sip of my fizzy water, and I'm going to look at the time and realize actually I'm done quite well for time. Blueberry pomegranate. Okay, so what I'm going to do is I'm going to erase this middle one to make room for the calculations for this shape over here. Now this shape over here is a little bit tricky. I find it a little harder for us to see for sure what shapes can we put together to form this composite shape. But there is enough information so that we can figure it out. Let's erase this. Okay, what I'm going to do is I am going to connect this point right here at the end of this 16-inch length that we are given in the drawing. I'm going to connect that point up to here, and I see that I have a right triangle. I should have put a little right angle symbol there, so I'm putting it in now. Okay, so I have a right triangle and I have a parallelogram. If this is 16 inches and that is 16 inches, I can see that I have evidence that this is a parallelogram. The height of that parallelogram is 8 inches. So I'm going to be combining the formulas for the parallelogram area and the triangle area. Something's missing. I have another quick little calculation to do, which is if this whole thing is 22 inches and this part is 16, I can subtract 22 minus 16 equals 6, and that means that the base of this triangle over here is 6 inches. Now I have enough information to get going. Okay, the area of the composite shape will be the area of a parallelogram, which of course is base times height, plus the area of a triangle, which is base times height over 2. Now it's interesting because the shape seems so strange. It seemed really challenging at first, but once we get to this point where we've decided what smaller shapes we are putting together to make the composite shape, then we look at the area formulas and it doesn't seem so complicated after all. Base times height for the parallelogram is going to be 16 times 8 And base times height over 2 for the triangle is going to be 6 times 12 over 2. 16 times 8. 8 times 10 is 80. 8 times 6 is 48. 80 plus 48 is 128. Then I have different ways I can simplify this. I think I'll cancel a 2 from down here and from the 12, which will turn that 12 into a 6. So I end up with 6 times 6. I have 36. More than one way of simplifying that. 6 times 12 is 72, divided by 2, that's 36. Okay, that works as well. Okay, 128 plus 136 is giving me my final answer. 120 plus 30 is 150, and 8 plus 6 is 14. 150 plus 14, that is 164 square inches. I did it. So, it seems like, okay, we've only used 11 minutes of our lesson, and we've done 3 shapes, and it seems like, okay, this is easy, we know what we're doing. Is this the only thing that can happen with composite shapes? Though, no, because sometimes a composite shape is formed by adding together smaller, simpler shapes, but sometimes a composite shape is found by subtracting. So I need to do some examples like that. Now, this is where things will take a little bit longer because I started the lesson with those 3 shapes already drawn. The next bunch of shapes I'm going to do, I have to draw while we have the camera running. So let's get into it. One at a time. I need to do some erasing. So you guys were fun, but I don't need you anymore. I need to make room for the next shapes. Thank you very much. 3 interesting composite shapes. You have done your duty. Next one is going to start, and I guess I shouldn't be always saying what the shape is. I want the students to see the diagram and be able to figure out what the shape is. But I'm going to start by drawing an 18-inch line. Let's see, I'll put it over here and I'll do the calculations over on this side more. 18 inches, there's an 18-inch line. Okay, that's a start. And then I am going to, by eye, create a right angle, but I can double check it with the protractor if I really want to. And I am going to, oh, it's going almost all the way up to my geometry heading. I am going to draw another 18-inch line. Okay, it was a little crooked, but I got it. Okay, so maybe you can start figuring out what shape it is that I'm doing. Another 18-inch line over here. There. Try and make it nice and perpendicular. And then finally I am closing this off at the top with another, wow, it happens to be another 18-inch line, which is a good way for me to verify that I've done right angles when I wanted to. But I can also verify with my protractor. Yes, 90 degrees, yes, 90 degrees, yes, it's looking good. Okay, so, how do I want to draw this? I'm going to put the little symbols on the corners. And I think the students have probably figured out now that so far our shape is a square. If that were all there was to it, we would just have to know the side length and the square and we'd be able to find the area. But that is not all there is to it, because I need to draw a circle. I'm going to trace. I'm going to trace this thing. Let me see how long it is. I think it's just about the right size. Oh yeah, that is exactly the right size. Okay, so I'm going to trace this thing. And that's convenient because I have a nice little circle inside my square. Now the composite shape is the shaded area I have to shade. So I'm going to shade so we can see the shaded area that I am talking about. Okay, not too complicated a composite shape, but to find the area of the shaded part, we can't just find the area of the square. We have to find the area of the square and then subtract the area of the circle. I need more information. I need some dimensions. So I'm going to create our little radius, and I am going to draw it inside my circle, and I'm going to label it with its length, which is 3 inches. I'm also going to label 2 of the sides of this figure just to make it really clear that it is indeed a square with 18 inches. Okay, now we know what to do. It's really the same math. We are combining two area formulas into one. It's just this time we have to subtract. So the area of the composite shape is going to be the area of the square, which is side length squared, minus the area of the circle, which is pi r squared. We can do this. The side length is 18. So I have 18 squared minus pi. We're using 3.14 for pi. The r squared is 3 squared. Let's simplify. Where's my calculator gone? Ugh. Lots of chalk dust on this thing. Okay, 18 squared first. 18 squared is equal to 324. Minus, okay, I'm going to do this in steps. 3.14 times 3 squared. 3 squared is 9. Why do I multiply the 3 by the other 3 first and not multiply the 3.14 by the 3? Because I want to follow the order of operations. The 3 is being squared. It is an exponent. An exponent is supposed to happen before multiplying, so I like to do that. I like to diligently follow the order of operations. So we have 324 minus 3.14 times 9. 3.14 times 9 equals 28.26. And when we do this subtraction, we are getting 295.74 square inches. So really the only thing that was different is that we had to subtract. Or is it the only thing that was different? If we just look at the silhouette of the overall shape, it's also different because instead of having some weird alien shape like we've never seen before, we have a square. But we have to notice that this part is not shaded, and that's what indicates we have to subtract. But we're just putting together area formulas that we already knew. So a lot of this really is a review, and it's valuable extra practice of working with those area formulas, telling apart the different shapes, remembering what type of math goes with the different shapes. And then you can piece together the work that you have to do to solve the overall problem. Because even this, it looks complicated, but I'm really doing one thing at a time. When I do the 18 squared, I do that and I'm able to get its answer. I'm not really worrying about the circle while I'm doing that. When I move over to the circle, I'm no longer worrying about the square. So even if this becomes much more complicated, which it will, sometimes maybe, with more than one unshaded area inside the big shaded area, you can sort of focus on one shape at a time while you're doing your calculations, and that helps to make it a lot less intimidating. Okay, I'm doing okay for time. I want to do another one. And we're going to do another composite shape, which is going to involve subtracting, which means I'm going to be putting shading in again. Okay, erasing all this. I'm going to draw a triangle, and I'm going to give you information right away that it's going to be a right triangle. I'm going to start by drawing the height, and that's going to be 20 inches. Where's my 20? There. 20 inches. And my base is going to be 30 inches. This is going to be quite a big right triangle. So I'm judging by eye, but I'll double check with my protractor afterwards. This ruler only goes to 24 inches, so I have to move it and set it up again and make the line a little longer in order to get that 30-inch base I wanted. Okay, this is 30 inches. Not leaving myself very much room for the calculations. I can finish drawing this triangle. I have to be careful. You know what I'll do is I'll take this. Could have done it all along with this thing. It's longer. I can take this thing and I'm going to put in the hypotenuse of my right triangle. Now inside of this, before I put any shading, make sure to put that, I am going to put another triangle, but this one's going to be equilateral. That's interesting. And I don't want to arrange it too neatly. I want to be creative about where I place the base. So I'll put the base sort of almost horizontal, but I'm going to have a 10-inch base. Can I fit a 10-inch side length equilateral triangle inside this right triangle? Well, we're about to find out. I need my compass. I want to draw this properly. So I already know that line is 10 inches long. I'm going to use that to measure, and then I'm going to do this. Oh, it's just barely going to fit. And the point where these two arcs cross is going to be the third vertex of this equilateral triangle with a side length of 10 inches. And one more. Okay, so we have 10-inch. Where should I put this? I'm going to put this on the. I'm going to put it on the inside, but over to the left of it because I want to be able to draw my height. I don't know the height of this. It's got a 10-inch base. It's got a 10-inch side length, but I need the height to do the area of that triangle. So what I'm doing is I am marking the midpoint of this 10-inch base at 5 inches, and I am drawing a height. I'll use a dotted line, and I'll show that that is a right angle to show that it is a height. And then I actually did the calculation ahead of time, didn't I? Yes, I did. But no, you know what? I'm realizing this is a Pythagoras situation. The students who are learning this lesson are supposed to already know their Pythagoras because I just taught it 2 weeks ago or 3 weeks ago. So we'll use Pythagoras to find the height of this small right triangle. I also need to show my shading. The composite figure that we're trying to find the area of is the shaded region. So I'm shading inside the bigger triangle, but not inside the smaller one. Okay, now we have to find the area. I finally have this problem set up. Okay, so without using a ruler, I'll do a little diagram of the smaller right triangle, which is meant to represent half of this equilateral triangle. Its hypotenuse, I'll draw the little square so that we see it as a right triangle. The hypotenuse is 10 inches. And then since I had to cut this bottom base in half, that means this is 5 inches. We have a Pythagoras situation, so we can find this, which will be the height that we need for our area formula. So we have an extra step again, but it's a little bit bigger of an extra step than in some of the previous questions. So Pythagoras is going to be hypotenuse squared is equal to a squared plus b squared. The hypotenuse squared is the 10 squared, and it's going to be equal to, one of these is a, one of them is b. I'll say a is 5 squared plus b squared. I am going to solve for b in order to know the height of my triangle. 10 squared is 100, 5 squared is 25. So quite a lot of page is used just finding the height of this little triangle so that we can do the rest of the problem. 100 minus 25 equals b squared. I'm employing a bit of algebra skills. 100 minus 25 is 75. So therefore b squared is equal to 75, and b is going to be equal to the square root of 75, and that is going to be 8.7. This is rounded. So it rounds to 8.7. Okay, finally, after all that work, I have enough information to do my composite figure, and I have enough space over here. The area is going to be base times height over 2 minus another base times height over 2, which will be equal to 30 times 20 over 2 minus the base is, now we're doing the base of the entire equilateral triangle. A lot of students I know would say, okay, the base is 5. Well, we don't really need the area of just this little bit. We need the area of the whole thing. This is half as big, so there's more than one way of doing it, but I like to just go back and say, okay, my equilateral triangle that I actually need to know the area of has a base of 10 inches, which is written a little off to the side so it looks weird, but I'll just have to apologize for that. 10 times, and then the height is the 8.7 that we got with Pythagoras. Put a squiggly line to differentiate between my calculations and the label here. And I still have to write the over 2. Okay, 30 times 20 over 2 is going to be 300, isn't it? I walked off the camera. Okay, so 20 divided by 2 is 10 times 30. There's different ways of showing this, but it's going to be 300. And then we have 10 times 8.7 over 2. 10 times 8.7 is going to be 87. And 87 divided by 2 is going to be 43.5. Yes. And we did it. 300 minus 43.5 is going to be 256.5 square inches. We did it. Doesn't matter what shape you have as your big shape that you're subtracting from, so long as you know all the different shapes and you know how to use the area formulas. Doesn't matter what you have as the smaller shape that you're subtracting. We know all the shapes. We know all the area formulas. Interesting drawings can be made by combining any shapes that we know. In this case, it sounds like it was just too straightforward and not very interesting. A triangle inside another triangle, but frankly, I think this is interesting because of the fact that we know so many different types of triangles and we're ready to deal with them and we know how to apply Pythagoras' theorem when we need it. So 256.5 square inches, that is my final answer for this one, and it is time for me to move on and use, at least, I'm going to do another composite shape, another one with the shading and the subtraction, and I'm going to use two of the shapes that we've already used in this lesson. How am I doing for time? I'm doing great for time. Okay. Erase. After all that beautiful drawing, it just feels like such a shame to have to erase it all. There. Okay, so what I'm going to do now is I am going to draw a parallelogram with a base of 20 inches. How high is it going to be? Not that high, so I can put it over here, put it like this, 20 inches. That's good. And then I have a height of 10 inches, so I'm going to mark that on the outside here. Now, how do I want to construct this? I guess I have a lot of flexibility as to how I construct it. So long as I know the height of the parallelogram, I can change my angle quite a bit and it doesn't change the area. That's interesting. So long as I get to the same height, okay, how about I do this? Now, to draw this one at just the right angle so that this side is parallel to that side, that's tricky. But I find it easier to do this. I am going to draw another 20-inch base for the top of my parallelogram. I'm judging by eye that the edge of my ruler is parallel to this. And I know it has to be 20 inches long. 20, where's 20? There it is. So this fourth side that seemed like it would be tricky to draw isn't so tricky because I drew it last. Okay, we have a parallelogram, but it's not a composite shape yet. We need something inside it. And inside it is going to be a trapezoid with a base of 8 inches. I wonder if this will even fit. Let's find out if it's going to fit. I'll move it over a little bit further. I think I can make it fit. 8 inches. Okay, and the height is also going to be 8 inches. Oh, this is just barely going to fit. But it fits. Now, I want the small base of the trapezoid to be 5 inches. And then I can connect the endpoints of these two lines. To finish it, I will show that it is a right trapezoid with these little right angle symbols. And I have to label it. So this is 8 inches. This is 8 inches. This is 5 inches. We have all the information we need. Do I have to do any subtractions? No, I don't think so. I need to shade. we're able to do the composite shape. The area is going to be equal to the area of a parallelogram, which is base times height, minus the area of a right trapezoid, which is 1/2 times base 1 plus base 2, times the height, which is, base times height is 20 times 10. I don't need to be holding this anymore, I'm putting it down. And then, minus 1/2, base 1 of the right trapezoid is 8, and base 2 is the 5, and the height is another 8. Simplifying, 20 times 10 is 200, minus, I'll show 1/2 times 13 times 8. More chalk, please. 200 minus, half of 8 is 4, 4 times 13 is 52. 13 is, yes, 52. Okay, 200 minus 52 is going to be 148 square inches. Not so bad. It's starting to seem kind of routine, isn't it? That each of the 6 shapes we've worked with in this lesson so far have involved 2 area formulas. The bigger one and the smaller one, which are necessary if we are subtracting because the composite shape is asking for the area of the shaded region. And then when the first 3 examples, it doesn't really matter if one of them is bigger than the other because we are making a composite shape by adding together 2 of the smaller shapes, and we do an addition. So what can I do to make this more challenging? Nothing. Nothing will make it more challenging. The students know everything they need to know to be able to do this. You just have to pull out the area formulas that you need for the situation. And it's hard to say ahead of time exactly what you will do because it sort of depends, right? It depends on whether the composite is an addition or a subtraction. It depends on which shapes are being added and subtracted, and that gives us a tremendous amount of variety. So the thing I want to do next is I want to draw a bigger composite shape where we're going to do the shaded region, but instead of having just one small shape on the inside, there are going to be several. Let's see, with the amount of time that I have, let's see how complicated a situation I can create, which all of us know really actually isn't complicated. The point of it being that you realize that you can do each area formula by itself and just ignore everything else while you're doing it. You can do the problem in pieces, and that means it's not really any harder than the smaller problems that we started with before. Okay, so I'm going to make the outside big giant shape that's shaded is going to be a rectangle. But then I'm going to try to incorporate quite a few of the other shapes on the inside. That's going to be the challenge. The ideal way to do this is if there were students here, and I would ask the students, okay, name a shape. Okay, name the dimensions for that shape, and then just do whatever the students suggest. But I don't have students here, this is a video, so instead I'm going to do it myself. Erasing. And another thing I'll do is when I draw my rectangle to start with, I won't measure it. I'll measure it after. So therefore I might end up with some bases and heights, well, at least base and height for the rectangle that might have, fractions and decimals. You could have like a 20.5 inches or a 20 1/4 inches, but there's nothing wrong with that. We can handle that. So let's see, let's fill this. Now, another thing I have to be concerned with is I have to leave enough room for all of the calculations, and there will be quite a few of them. So what I'm going to do is I'm going to start my rectangle here. Yes, here. And I'm going to make it quite long. And, well, the height is quite long, and the base is going to be even longer. Which means I have to move the ruler and extend this line. I think I can safely make this fit inside the video rectangle. Yes, I can. Might even have room for a few calculations over here, and we might need the room. Okay. This is hard to do. I want to make sure I have a right angle here so that I really have a rectangle. So that'll help. Getting my protractor out helps. Doing things by eye is fun, but the larger the shape, the harder it can get to do a freehand drawing. Even this is tricky. Oh, that got crooked all of a sudden. Hang on, I'm gonna get it. There. It's a little messy over there, but we're good. Now, to connect these two, will I actually have another right angle? I certainly hope so. Just quickly check my right angles. Yeah, that's good. Yes, that's good. Yes, that's good. Okay, so I'm going to put the little right angle symbols on all of the corners so that people can see that it is a rectangle. We have our outer shaded shape, but I can't shade it yet. I have to draw some smaller other shapes inside it. Now, what shapes can I do? And I want to fit quite a few, so I want to, put shapes close to the corners. Some things don't fit well in corners, like a circle wouldn't fit very well in the corner. And I don't want to use the exact same size circle either. How many different shapes? Well, let's think about triangles. Okay, I'll start with triangles. We have what types of triangles do we know? We know the equilateral triangle. We know the isosceles triangle. We know the right triangle. We know the scalene triangle, but the right triangle could also be a scalene triangle. An equilateral cannot be scalene. An isosceles cannot be scalene because the scalene triangle has to have 3 different side lengths. But the right triangle can have 3 different side lengths, so that would be a scalene triangle too. But here's one. This is a fun one. I'm going to trace my set square here, and I'm putting it way over near the corner so that I can leave a lot of space for other shapes. Move hands out of the way. There. Okay, so these corners look a little roundy, but they're not. They're pointy. I'm going to put a right angle symbol here. This is the 45 degree, 45 degree, 90 degree triangle that is a standard for a set square for carpentry, but also one of the set squares that you tend to get in all geometry sets will be the 45, 45, 90. So what I have here is I have 2 types of triangle in one. I have an isosceles because these 2 sides are equal length, and I also have a right. So I manage right and isosceles. That's what I'm going to do over here. Right triangle, isosceles triangle. Is that fitting? Yes. Check and check. So by putting a right isosceles triangle in, I covered 2 of the triangle shapes that we'd like to cover. And I also started with the rectangle. I think I'll write that up from the top. Not too messy. Rectangle. Oh, it's still messy. It's hard to write way up here. Check that off. Does that fit in the rectangle? Does the rectangle fit in the rectangle of the video? Yes, it does. Okay, so I need to put some more in. What other triangles? I want an equilateral triangle. So I already used one with a side length of 10. I want to choose a different side length. I'm going to draw an equilateral triangle using inches. I'm trying to do everything with inches, but we'll see. We're going to measure these afterwards. So I used 10. I'm going to try using 8. So there's an 8-inch side length, and I'll label it here. Can't really draw an equilateral triangle without knowing the dimensions, so it's not really a mystery. Let's get this ready and then draw some arcs. But this drawing can get very messy, so as soon as I put a point right here, I'm going to erase the rest of the arcs because we don't need the arcs to show in our composite drawing. At the end, we need to know where that point is so that we end up with a proper equilateral triangle. What's this metal thing got stuck to the magnet on the back of my ruler? Okay. Okay, we have an equilateral triangle. And that's going to be 8 inches, that's going to be 8 inches. I don't really want to clutter it up with too much labeling though. We also need to figure out the height of this triangle. Maybe we'll just do that by measuring this time though. Okay, so we have 3 triangles. Well, we have 2 triangles that cover 3 of the types of triangles. This is an equilateral. Check. What am I missing? I am missing equilateral isosceles, right, and we have the scalene. I'd like to put a scalene in there. I'm not going to do an obtuse triangle. Those are too hard to label when you're putting together this type of figure, but we could if we were to take enough time drawing, we could. I'm going to put in another right triangle. This is a right triangle, but I'm going to put in another right triangle just to make sure that I have a scalene. So what I'm going to do is I'm going to start with a hypotenuse, which I'll put there, and then I'm going to draw the base, and then I'll make sure I have a right angle with my protractor. I'll have to complete one of these lines later. There. Okay. Let's see how much time I have. The trick here is I'm going to use a lot of time with drawing, but I have to save time for the calculations. I don't want to get this all put together beautifully and then have to give it as homework. I'd like to actually finish the demonstration. So, drawing this is not isosceles. This is not isosceles. It's not that different looking from this isosceles one we have up there. So we're going to have to prove it's not isosceles by measuring. So I'm going to measure right now. I'll label the base and the height. Ruler. The base is 7.5 inches. I have to write fairly small. And the height is not it is 6 inches. So we probably have a good feeling that the hypotenuse is not going to be equal to 7.5 or 6, don't we? Yes, we have a very good feeling. If we understand right triangles, we're feeling, oh, it actually happens to be exactly 10 inches. So this is scalene. I'm not labeling the 10, we don't need it. We have what we need for our area formula. But we have a scalene. I'll put SCAL dot TR dot, check it off. Okay, I've covered all the types of triangles that I want. And I have lots of room for other things. And we have some of the dimensions we need for our area formulas already, and we'll measure to get others. I have a rectangle, I need a square. I want a square. And I can fit a square nicely into the corner. Now, how long was that side? Pretty good for freehand. Oh, except when your chalk just goes crooked on its own and doesn't stay close to the edge of your ruler the way you wanted it to. So that'll have to do. And I already know the measurements, so I'm going to give it. This is 6 inches. This is 6 inches. It is a square that is 6 inches aside, and I know I've already used one of those in this lesson, but I don't care. It was convenient. Okay, rectangle. And rectangle, not rectangle. We have rectangle. Square. Square. Check. Okay. Parallelogram. One parallelogram will be enough. So I'm going to do, and this time I'm going to freehand draw it. Let's see. Now I can't freehand draw it because I want to make sure that it's really a parallelogram. So what I'm going to do, where's that? Oh, can't see. Okay, there. Just judging by eye that these are parallel. This is going to do it. Okay, we have a parallelogram, and I'll get the dimensions later by measuring. Parallelogram, I'll just put that. Check. We need a couple of trapezoids, don't we? We need an isosceles trapezoid and a right trapezoid. I want both of those in there. And once I have them in, I think it's going to be time. Very soon it will be time to start doing our calculations. Otherwise I'll run out of time. 15 minutes left. Okay, I want both of these. Let's get them in there. Right trapezoid. Right trapezoids don't always have to have the bases on the top and the bottom. So I'm going to quickly, judging the parallelism by eye, I'm going to draw a right trapezoid like this. Label those so that we know they're right. I may as well label these as well. Okay, so that is a right trapezoid. We'll figure out the measurements later. I want an isosceles trapezoid. Check off the right trapezoid. Isosceles. Now that's tricky. That's tricky because I want to make sure that the basis, small base is centered. So I'm going to cut 2 inches off of each end. Can't see. There. Okay. Okay. That should be good. I'm going to do this. And do this. It's a little sloppy looking. There. Put little right angle symbols. We have an isosceles trapezoid. It's not the best drawn one I've ever seen. And we need a circle. I don't want to use the same circle. I don't want to use this. Wait, here. Yes, this is not the same size. Let's trace this to get a circle because that'll be a nice fast way to get a circle into our drawing. And I'm going to judge a center, draw a radius, and we'll measure the radius later. Circle. Check. And isosceles trapezoid, check. Have I done everything? Square, rectangle, parallelogram, 2 types of trapezoid, 4 types of triangle that are covered by 3 triangles. Circle. That's it. I think that's all the shapes that we've been working with. So, very complicated. It's time for me to put in some shading. Actually, could make this whole diagram become very messy. So I don't want to overshade. I'm wasting a lot of time just doing this shading. Okay, I think I'm getting messier and messier the further I do this. Okay, we can see the shaded region. We can see that we have a large rectangle. We have to find its area, and from that we have to subtract 1, 2, 3, 4, 5, 6, 7, 8 other areas. This is going to be a big calculation. But I'm going to do it in pieces. Instead of trying to write area equals this minus this minus this minus this. No, I'm just going to do all the area formulas bit by bit. And I'll start here, and I'll start with simple one. Area of a square is equal to side squared, which is 6 squared, which is 36 square inches. There, I did one. Okay, the area of the rectangle, I have to measure to do the area of the rectangle. How big was this rectangle after all? That's 24 inches, and this 36 inches. How about over here? How far can I go? Doesn't matter if my head stays on the screen. Area of a rectangle is equal to base times height, which is equal to 36 times 24, which is equal to, I'll get my calculator, I am going to run out of time if I'm not careful. 36 times 24 equals 864 square inches. We have 2 of the 9 shapes that we have to find the areas of. How long is the area, how long is the radius of this circle? It's 3 inches. It's the same size as I had before. Well, that's not interesting, but I'm just going to go with the 3 inches. The area of a circle is equal to pi r squared, which is 3.14 times 3 squared, which is 9 times 3.14, which is 28.26. Is it 28.26? 9 times 3.14. Yes, 28.26. 28.26 square inches. Actually, this is going fairly quickly. We have 3 already. Let's do our parallelogram. That's a pretty easy formula. It's similar to the rectangle formula. Area equals base times height. But in the parallelogram, the base is 12 inches and the height is 6 inches. 72 square inches. Now, what should I do next? This triangle. That is 8 inches, and it is isosceles, so the base and the height are both 8 inches. Area equals base times height over 2, which is 8 times 8 over 2, which is 64 over 2, which is 32 square inches. Another triangle. We have the base and the height sitting here. Let's do it. Area equals base times height over 2, which is 7.5 times 6 over 2, which is going to be 7.5 times 3, that's 22.5 square inches. We can do this. We're doing it in pieces. I would be very confused right now if I were trying to think of everything at once, but that's really the point of why I wanted to do a problem like this one. I don't have to think about everything at once. I have to have an overall strategy, but I can focus on each area formula one by one. So that's 2 of the triangles. We need the third. This is going to be the one that's the... No, it's not. If were going to calculate the height using Pythagoras, then it would be a little bit more trouble. But I'm not. I'm just going to say this is an 8-inch base. I trust that. I drew it. And yes, that's 8 inches. So the height is going to be about 7.5 inches. I don't know if that's perfectly correct, but I'm not using Pythagoras. I'm using measurement this time. So the area equals base times height over 2. Let me double check that. It seems like 7.5 seems long. Let's see. Is that clearly 8? It's more like 7. More like 7. So I'm going to call it 7. So 8 times 7 over 2, which is 56 over 2, which is 28 square inches. Okay, there were 9 shapes altogether. 1, 2, 3, 4, 5, 6, 7. We already have 7 of them. We've done everything except the 2 trapezoids. I want to leave room for my big subtraction at the end. Here, I have room here? Not really. Maybe I'll just erase something to do the big subtraction at the end. So I'm going to do the area of, will that fit? That fit? Yes. Area of a trapezoid is 1/2 B1 plus B2 times H equals, which one should I do first? For both of them I have to measure. So I'll do the right one first. This is 11 inches, and this is 9 inches, and that is yet another 6 inches. Will this fit if I go underneath? Yes. 1/2 times 20 times 6. That's going to be 60. 60 square inches. We did it. I'm going to have room for everything except that big subtraction. Couldn't have planned it more imperfectly if I had tried. Time-wise, I'm doing pretty well with the time, so I'll just congratulate myself. I'll pat myself on the back for planning the time for doing this well, even if I didn't plan the space that well. Oh, but I might have a solution to that problem. Okay, area of the other trapezoid, that's the isosceles. 1/2 B1 plus B2 times H equals 1/2. Have to measure 12 inches, 8 inches, and the height is 5. 12, am I in the way, plus 8. My handwriting's messy when I do it this way, times 5 equals 12 plus 8 is 20, half of 20 is 10, 10 times 5. Oh, it's an easy calculation in the end. 50 square inches. I'm ready. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, wait, is it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not ready. I'm missing one. Which one am I missing? I have my parallelogram. I have my square. I have my circle. 1, 2, 3, 4, 5, 6, 7, 8, 9. Which one am I missing? Oh, this is awful. Is it this? No, I did that. That's the 8 times 7 over 2. I did the 7.5 times 6 over 2. There's the 8. So I did all 3 triangles. I have my circle, I have my square, I have my rectangle, I have my parallelogram. I have 2. That's what. Oh, and I wasn't even standing on camera while I was thinking about that. There are 10 shapes listed because one of the shapes is actually covering 2. I forgot. My isosceles triangle also happens to be a right triangle. So, and my right triangle also happens to be a scaling between them. That's why there seemed to be an extra shape that I hadn't found the area for. So now I can actually do my subtraction, and I have just about enough time left to do it. The problem is the space. So how can I solve this problem? We will be creative. What we will do, and this is going to involve some messy handwriting on my part, because as you may already know, I'm at my worst when I'm writing really low on the chalkboard. But what we will do is we will move the camera further and tilt it more this way. Having trouble getting it set. So the whole thing's still there. You see more clutter and furniture, but I have some room on the bottom to do a big giant subtraction. So let's write it. Okay, final area is equal to rectangle's area, which is 864, minus, okay, let's go this way so that I don't forget anything, minus 72, minus 32, minus 22.5, minus 28, minus 60, minus 50, minus 36, minus 28.26. Does that all fit? This video is kind of messy to look at, but yes, it all fits. 1 minus 1, 2, 3, 4, 5, 6, 7, 8 others, not 9 others. So I have everything. All I have left to do is to calculate. You know, this feeling I'm having right now, I want the students to notice. I feel a sense of relief right now because I gave myself this big assignment, and if I mess it up at the end, I just filmed for half an hour for nothing. So that's how I'm feeling. But I'm relating that to what students might feel when they're given a great big task like this, a great big multiple step geometry problem, and reminding you that we did it in pieces. Each of these pieces, the drawing of each piece, and then the area formula for each piece, was a painless, little, simple, fun thing to do. And even this at the end, this very important, big, giant subtraction equation, that's all I'm focused on right now. I'm doing all these subtractions without having to do all that other work right now because all of that work is done. A lot of the pieces of the problem are done. Now all I have to do is get into my calculator and do a bunch of subtracting. 864 minus 72 minus 32 minus 22.5 minus 28 minus 60 minus 50 minus 36 minus 28.26 equals 535.24. I want to write it. I want to write it way down. I'm going to do it here. 535.24 square inches is the answer to my problem. What is the area of the shaded region in this great, big, complicated composite shape? And I look at it with pride, and I look at it without regret, because I realize I didn't make it too complicated and scare away the students. I don't think any of the students are scared right now. They all know that they could do this too. Do it in pieces, don't panic, don't try to think about everything at once, and we will get to the end. And we have gotten to the end of this lesson. We went over by 45 seconds. So it's time for the dog, who is only thinking about her supper, say goodbye. It's time for me to say goodbye. She's uncomfortable. Okay, now she's comfortable. Thank you very much for being here. It was fun as usual, and I will see you next time.